scientists who are trying to bridge the worlds of natural and social sciences. And so for those of you for looking for ways to get into that world and that expertise, we'll certainly hear some of the research that comes out of that today. But I urge you to use that as a mechanism and entry point, and I'm sure Charles would be happy to do that. So let me turn the floor over first to Nils to get it started, and then we can go from there. When it comes time for the discussion, I ask that you wait for one of my colleagues to bring you a microphone. Let us know who you are, but use the microphone because we are webcasting this meeting live, and then the video will be archived on the web, and we want the folks online to be able to hear your question. In fact, folks online had a question yesterday that we plugged into the meeting, so they are watching and they are taking notes, so we want them to hear what you have to say. So Nils, please, the floor is yours.
Well, thank you, Jeff, for a very generous introduction and for the opportunity once again to meet in this project. I regard Jeff as the mother of all project organizers. This is a joint project between 3 different research centers, and I'll start with perhaps the more general introduction outlining some of the problems of the field, and then Marc and Charles will try to develop some of the answers, hopefully. My part of the presentation is developed with 3 other people, Halvard Bruhaug, Ole Magnus Theisen, and Henrik Urdal. And Halvard and Henrik are here over on my left and will participate in the Q&A. And we have a division of labor, so I'll deal with the easy questions and they will do the difficult ones. I'll start with and our focus is on resource scarcity and conflict more generally, but we'll focus today to some extent more specifically on water scarcity. Let's start with 2 quotes that express the conventional wisdom that in the policy community particularly, but also widespread in the academic community, the resource scarcity is a prime driver of conflict. We have Lester Brown, former head of the World Watch Institute, saying that what we're seeing across Africa now is that the herders who are on the southern edge of the Sahel are being forced southward into the agricultural areas. In Nigeria, it's a conflict between Muslim herders and Christian farmers. In Darfur, in Sudan, it's between Arabs and blacks. And all across Africa, that conflict is playing out. And we have Ole Mjøs, who's head of the Norwegian Nobel Prize Committee, who said a few years ago, after the award of the Peace Prize to Wangari Maathai, I predict that within a few decades, when researchers have developed more comprehensive analysis of many of the world's conflicts, that the relation between the environment, resource, and conflict may seem almost as obvious as the connection we see today between human rights, democracy, and peace. In civilian life, Ole Mjøs is professor of medicine. I've been wondering if I should make some predictions about the future of medicine, but I think I'll refrain from that. But water resources are, of course, among those resources most widely believed to be worth fighting over. It's an essential resource for human existence, and therefore there's some plausibility in the idea that it might be worth initiating conflicts over scarce water. Oops. Sorry.
Because it's that computer. Is it working? Okay.
Oh, but I need to look at this. I think.
Okay.
What's the empirical state of the art? In fact, we're finding fairly limited support for these neo-Malthusian concerns about resource scarcity and civil country when we look at the country level. We find that high population density does not generally increase the risk of conflict, and my colleague Henrik Urdal dealt with that in more detail in a lecture here yesterday. We find that high water scarcity does not generally increase the risk of conflict. We found that some resources are more hazardous when they're in abundance than such as diamonds and oil. But the abundance perspective, the resource curse perspective, probably does not apply to water. There's more support for the idea that rainfall deviations may lead to conflict indirectly or directly. The indirect link is that the rainfall deviation may represent an economic shock, which in turn will produce conflict. Our argument in this project is that we may find more support for the resource scarcity perspective and conflict if we move in 4 other directions. If we focus on the local distribution of resources, if we focus on intergroup conflicts rather than conflicts with the state, if we focus on changes in resources rather than the level of resources, and if we focus on the social and political and economic context of scarcity. And I'll deal briefly with these points in turn. Resource scarcity is usually not uniform across nations. It may vary greatly within the country, and this is certainly true of access to fresh water. There are also other catalysts of environmental stress that are likely to vary across space. There's the absence of state authority, particularly in weak states, which are also large states. State authority will be weaker as you move towards the periphery, away from the capital or the military center. Rapid population growth and migration will also vary a great deal within countries. Ethnic tensions. Ethnic groups are not uniformly distributed over the country. Migration from neighboring areas, including conflict migration. If you have a conflict in a neighboring country, that drives migration in and perhaps brings some of the conflicts, carries some of the conflicts with it. And lack of alternative means of livelihood are also not uniformly distributed. All of this calls for a more disaggregated research design. Secondly, we think we should focus more on intergroup conflicts, where the government is not necessarily a direct participant in the conflict. Most of the existing conflict data have been on state conflicts, either interstate conflict or intra-state conflict, civil wars. But we're beginning to get now some better data on intergroup conflicts. And this may be important because fighting the government is extremely costly. It may be easier for a group that's suffering from resource scarcity to fight another group and hope that the government will stay out of the fight. And again, this is particularly likely to happen in peripheral areas of the country where the government is weaker. So we have the desert versus the oasis syndrome. We have nomads hit by degradation, drought, etc., who migrate to more fertile ecozones. And this leads to conflict between locals and newcomers, and between farmers and herders. And this is, of course, the perspective that's been applied to the Darfur conflict, as we saw in the initial quote by Lester Brown, and to some extent also in Nigeria and a number of other African countries. So here is a graph of some intergroup conflicts in Africa from 2002 to 2005, based on data from the Uppsala conflict data project. We see that most African intergroup non-state conflicts occur along the southern edge of the Sahel, where people are vulnerable to deviation in rainfall, and where it's also high population density. This belt actually also has hosted a number of intrastate conflicts, in other words, conflict of the more traditional state kind with the government, that have caused massive population displacement, which in turn might lead to further non-state conflicts. Now, a third perspective is that change may be more important than the level of resources in the resource scarcity perspective. We know that humans adapt to the environment, but slowly. So particularly rapid changes in scarcities are more likely to cause disruptions, including conflict. So societal instability and intergroup violence is more likely to occur in regions with significant and rapid environmental change. And environmental degradation is also likely to have considerable externalities, for instance through forced migration. And so my final point is that the effect of scarcity is contextual, that environmental scarcity by itself is an insufficient cause of conflict, but that governments may mediate or accelerate societal impacts of environmental change. If there's a drought in Hungary, a reasonably competent government is assumed to be able to handle it by shifting internal resources, by calling for international aid, and so on. In a country with Ethiopia, with a much less competent government, with internal conflict already, and even more strongly in countries that perhaps fail to have a functioning government at all, these things are much likely to have disastrous consequences. A classical example is contrasting India and China with regard to famines. This, of course, is Amartya Sen's famous example, that although India has had many droughts and many cases of crop failure, they've never had a disaster since becoming independent on the level of the Great Leap Forward in China, which was caused and indeed made stronger by incompetent government policies. Tropical storms in Haiti versus Dominican Republic. You can actually look at a satellite map and see the different impacts they have in the two countries, which can be traced back to, again, government policies. Poor and war-torn societies are not that well equipped to handle scarcities, so there's an interaction between resource scarcity and previous conflict. And the final point on the contextual effect of scarcity is that if structural scarcities overlap with other intergroup inequalities, for instance, ethnic marginalization, this may produce a particularly conflict-prone measure. So these are the four directions in which I'd like the research to move, and I turn the floor over to Charles and Marc to explain how we've started doing that.
Thank you. Okay, I'm going to pick up here and shift gears a slight bit. I'm going to be representing the Earth System Science community, in particular members of our community who provide geophysically based information. And in the context of talking about climate change and water resource stress, it's going to be my job in this team of 3, recently funded by the National Science Foundation's HSD, Human Societal Dynamics program, to bring some of these ideas together in a quantitative way. So I'll be providing you with a little bit of our thinking about how to merge geophysical data sets having to do with the water cycle, or what we often call the hydrosphere, with the social science data sets in order to uncover some of these patterns of conflict. Whoops, you want to do that? Thanks. As our previous speaker alluded to, there may not be simple relationships targeting a resource stress in the outbreak of conflict. And if we look at how water plays into societal vulnerability, there are many different ways in which water interacts with vulnerable human societies. We could talk about the provision of, or lack of provision of, sanitation and clean water as a potential stressor. We have all sorts of food security issues wrapped up with the availability of water supply. Floods and hazards certainly are embedded in the water system of our modern day. There's also a very important set of ecosystem services that are derived from our water resources that is absolutely critical to preserve. So water is necessary for development. And as we use water, we also pollute water. We create stresses that way on both ecosystems and humanity. So there's a panoply of challenges facing us as we look at water resources globally. Some of these issues may actually play out in terms of the conflict realm. In terms of what Earth system science can kind of bring to the picture here, over the last, I would say, 15 to, let's say, 20 years, there's been a concerted effort by the community to develop a richer understanding of how the Earth system operates, and in particular with respect to how hydrology and the water system operates. We've made very, very great strides. There's a host of geographically specific data sets that we rely on, increasingly sophisticated models that are able to map out patterns of water supply that are both abundant and scarce. And we've really brought to life what we sort of can view from our windows in our backyards to really begin to articulate global scale syndromes and patterns of water scarcity and water stress. And I'd like to just kind of review some of the progress that the community has made. Now, in my attempt here to mesmerize the crowd and get you on my side, I'd like you to just stare at this this image here that comes to us from the Earth system science community, and it's the results of a global circulation model. And what we're showing here in white is the moisture that's held by the atmosphere and that could potentially rain or show up as rain or snow. And wherever you see a little orange area, that's where it actually is raining or snowing according to this model simulation. And I think it's quite remarkable that as you look at this, you pick up honest-to-goodness features of how the real world is operating, and you see all sorts of very rich, chaotic behaviors and these really amazing clouds forming really wonderful integrated picture of how the water system operates. And I think we're at a point in our development as a science where we could really begin to think of very concrete applications in the social realm for this very physical picture of how the Earth operates. Just as next, please. Oh, okay. Just as an example of how such calculations are made, and just to give you a flavor for what's going on, maybe I could have the pointer. We routinely, and it's not just the group that I'm working with, but several groups around the country and around the world, in fact, run these so-called hydrologic simulations or hydrologic models. And they start with information such as the spatially distributed pattern of precipitation. They make estimates of how much of that water ultimately moves back to the atmosphere as evaporation. We can generate through our models an estimate of the excess water, which can then be used locally as a water resource or then flow within river corridors to ultimately create water resources that are very, very important at the river basin. And this little graphic here, this little animation, which is running slowly on that machine, but fairly quickly on the machine I'm looking at, is really capturing the essence of the water resource question. And we've really moved to this position perhaps in the last 5 to 10 years, where we can really articulate the space and time characteristics of this water supply. Next. Okay. Having demonstrated that the community can make these sorts of calculations, we want to create a bit more value added with respect to some of these social dimension issues. And one of the ways that we've been thinking about doing this is to create a formal procedure by which we can take small, what we call pixels or grid cells, on which we make these estimates of water supply. And we link these otherwise separate little pixels together through these river networking schemes. I've shown a couple of these very high resolution Earth system science data sets that now can really allow you to point to a position on the surface of the Earth, and it actually represents a place where you can identify geographic features with great specificity. And we take these kinds of maps and our estimates of local water supply, and we combine them and we make a series of calculations that now are beginning to embed the human perspective. So instead of just talking about the excess water that flows off of a small little pixel and that becomes what we call runoff, we can talk about how much of that runoff supports how many people and how many times those people use and reuse that water supply and impart pollution signatures, for example, into the mix. And so we now have a formal process to go from the geophysical realm and by combining these with social science data sets, come up with indicators of water stress. Now, why does this make any difference at all? And what I show at the bottom corner here is a view of the water scarcity issue as articulated by the United Nations 10 years ago. In 1997, there was a comprehensive freshwater assessment of the world that was provided by the United Nations. And they expressed areas of concern at the state level, at the national level. And as you might imagine, the coloration here is intuitive. Wherever you see a red area, like in the Middle East, you see severe water scarcity and water stress. And where it sequentially gets bluer, you have less of a problem. Well, this is an interesting macro scale vision of what's going on. However, if you look at a place like the United States, it ranked a light blue, which meant don't worry too much, not too much water stress in the United States. And you might argue because we're a highly developed country, we don't have to worry about such issues. But in point of fact, throughout our country, there are perhaps not armed conflicts about water, but certainly many, many legal conflicts having to do with water. And if you begin to look at the question from a geographical perspective, where you begin to look at water supplies and water usage statistics at a fine spatial scale, you begin to see patterns of hot spots showing up here in red and blue. Blue means no problem, red means big problem. And you can really see that this becomes not a single number for the United States, but in fact a very rich set of challenges that we can now begin to map at great specificity. Well, you can still ask, well, so what? Okay, we sort of know this from our fourth grade geography classes. Well, maybe so, but at this time it becomes critical to make sure that we can formulate the correct challenge. And these two set of circled numbers here, I don't expect to go over these in any detail, except to say that if you look at the world through the eyes of the United Nations back in 1997, you would have tabulated 500 million people suffering from extreme water stress. However, if you look at the question in a more realistic fashion, merging these geographical data sets from the social sciences and the geophysical perspective, you actually triple the number of people who are under severe water stress. In fact, when we first published these estimates, they were viewed with some disbelief, but they have since been corroborated by other groups taking a very similar approach. So this allows us to, I think, better articulate the problem at hand. So in terms of mapping out potential sources of conflict, well, here's one. This is a mapping that we've done to look at areas of the globe where the supply of water is insufficient to meet demand. And either this means that you forego whatever economic development you had relied upon for that water to provide, or you begin to deplete your aquifers, or you institute quite costly interbasin transfers of water, very expensive means by which you ship water around the different parts of the watershed. Or perhaps you desalinate, also a very expensive way to supply water. And what this is showing us from actually a geopolitical perspective is hotspot areas where we have depletion of water supplies, like in the central U.S., like in Australia. And these are two regions of the globe that export crops to other parts of the world. And one might ask the broad-scale question, how long can this go on in terms of shipping our water out, basically our water, out to other parts of the globe on a sustainable basis? Another potential source of conflict has to do with climate change and variability. And one of the elements of the climate change question is how much more variable will the climate become? Will we suffer greater drought? Will we suffer at the hands of greater floods? And in this particular case, for Africa, we've mapped out for the Nile and the Orange River two different conditions. One under which we look from the headwaters of the drainage basin right to the mouth of the drainage basin. So we follow the river downstream, and we can begin to pinpoint how much water stress we see as we're moving past different populations, as they're using more water, as they're abusing more of the water supply. And we can begin to articulate these, what we call fingerprints or signatures of human interaction with river flows. And the condition that we're trying to articulate here is the very great rise from average conditions to the condition of a 30-year drought. We can show this for the Nile River. We can show this also for the Orange River, or for that matter, any river in which we have sufficient information on water usage and human population. And we've now gotten to the point where we can begin to look at these questions in a very geographically spatial manner, and with, we think, fairly decent fidelity. In the next diagram, which should have, you might want to hit it again to get that animation going. Let's see. Okay, sorry. There is an animation there. What this is demonstrating is that we've now not only gotten to the point where we could take a better view of the recent historic past, but we could also begin to operationalize our view of potential stress points in the system. And if this were moving, you'd see daily precipitation events as articulated by a satellite called the Tropical Rainfall Monitoring Mission. It's a satellite that's been flying for the last several years, and with great spatial resolution and temporal resolution, it can tell us where it's raining. Okay? And for this particular analysis, what we did is a simple experiment of conjoining a population data set and a cropland data set. And we asked ourselves the question, how many times did the African population or the African cropland system get hit with potentially damaging rainfall? So this is not looking at drought, but it's looking at excess water. And we found actually a remarkable result with respect to the population, namely that twice the population of Africa had been hit with potentially damaging precipitation. And either this is wildly underreported in newspapers and the literature, or the kinds of standards that we've developed for the United States and Europe simply don't hold water in this part of the globe. And this is an open question as to how we interpret stressors in different parts of the world. Another, I think, very important and emerging source of conflict between humans or among humans, and conflict between humans and nature, is really going to have to do with looking at what's happening in the upstream parts of drainage basins and what happens in the midsections and in the coastal zones, the receiving waters. And just as an example of a potential source of conflict, there's enormous pressure on the land resource base of the globe to feed an expanding population with improved standard of living, improved diets. And there's going to be a lot of pressure on the land base. Clearing a parcel of forest for agriculture imparts a hydrological signature onto that landscape. And usually what happens is you increase the amount of water that flows off of that landscape. And you usually invoke a greater incidence of flood flows. So it becomes more intense, the runoff that comes off of these disturbed parcels of land. And you can begin to develop systems to take the land cover change signature, with darker colors meaning more historical change, and you could actually begin to assess how much additional water is being generated because of that disturbance and potentially flows downstream. And then if you connect to the populations that live downstream of these areas, you see that large fractions of the world's population live in low-lying floodplain areas. In particular, I'm looking here at the Gangetic Plain area. And certainly the impact of land cover change in the highlands reverberates into hydrologic signature and potentially reverberates into a vulnerability for large populations that live downstream. This also has very important implications on how much material flows to the coastal zone, so that as sea level rises, we don't invoke undue erosion on the coastal zone. We see this in many parts of the world, that impacts of trapping sediment behind reservoirs, for example, that impact reverberates fully into the coastal zones. Okay, that's my last slide, and I would like to now turn this over to Marc, who will engage some more of the social dynamic aspects of all this.
Thank you. So what I want to do is explain some of the empirical results that we obtained applying the analytical framework that Nils elaborated, making use of some of the earth science data that Charles just explained. Our group is based at Columbia University. It's another team effort. Two of our people are here today, Melandine Jaita and Christian Wiebersik, and there's other people back home as well. So the kernel of the original idea behind our work was to take advantage of the recent advances in the available data to try to answer some of these questions that have been lingering for a long time. So the hydrologic community had been a little bit further along than the socioeconomic community in producing a lot of high-quality georeference data sets that are relevant to questions of water scarcity. And then when PRIO started doing a degree of georeferencing to its conflict data, it became possible for the first time to put in a spatial framework questions about linking water and conflict. So the first thing that we did was to take the PRIO conflict data, which if you read it in a spreadsheet looks like any kind of tabular data that you might get, that you might be used to seeing in any kind of source, with the exception that there are 3 extra columns. There's a latitude and a longitude and a radius estimating the extent of the conflict zone. So from that, we can convert the data to a formal gridded time series database. My animations work.
Lucky guy.
One thing the socioeconomic community has ahead of it. So this is just animating that subnational conflict database. You can see that in some cases the conflict zones don't look that different from the old-fashioned view where the entire country might be coded as in conflict or not. But in other cases the subnational variance is quite big. So if you keep your eye on India here for a while, you'll see some geographically small conflicts pop in and out, up around here and so on. And so you have a much more precise geographic view of where the world is in conflict and where it's not. So some of the other socioeconomic data that we included are our population data set. So this is a view of the world's population using 350,000 census units as opposed to 180 some country units. So again, you get a much more precise view of where people are on the world. We also put a lot of effort recently in partnership with the World Bank to compile a consistent global subnational database of human poverty. In this case, we're using infant mortality rate as the proxy. This is the way you're used to seeing poverty rates portrayed on a map, one value per country. We took all the available subnational data and put it into a geographic database. And so we get this kind of view where you see much greater precision and spatial variation across the world. Even in areas where the data quality in general is not as precise as elsewhere, for example, through sub-Saharan Africa, we're able to improve on the baseline and get about 12 to 14 subnational measures of infant mortality per country. So this summarizes the hypotheses that we're trying to explore. And this is just another way of framing the views that Nils Petter put out at the beginning. We're interested in the conditions that obtain in a particular place in its own terms. So that's what we call here the absolute or standalone effects. What is this particular place like? And you can address that question in two ways. What is it like on average? Is it a very wet place, a dry place, medium? But you can also ask, what's that place like over time? Is it dry this year, but it was wet last year? So we have both the background effects and the variability effects. And we think that potentially both of those might influence the propensity for conflict across the world. And we're also interested in how a given place relates to its neighbors, the inter-regional dynamics. So we've articulated a couple of hypotheses here that might account for spatial patterns of conflict that have to do with differences across a given region in rainfall or resource dynamics. We've had less success so far in being able to implement tests of this because the information needs are more rigorous, more difficult to meet. It's one of our long-term goals to be able to do this more robustly. For the present, the results we're presenting have to do largely with these hypotheses. Are there hydrologic characteristics that explain the features of a given area that help explain the spatial and temporal conflict patterns found in that area? The first approach we took was to replicate in a gridded time series format a very common approach to explaining conflict outbreak. So what we did is we replicated a simple version of the political instability task force model that explains state failure, or in this case, a subset of state failure, an outbreak of civil war, as a function of a number of discrete factors. In this case, infant mortality, trade openness, and level of democratization, or the polity score. So high levels of infant mortality are associated with a higher risk of outbreak. Low levels of trade openness are associated with a high risk of outbreak. And a level of democratization that's in the middle, neither fully democratic nor fully autocratic, are also at higher risk. And we put these in here simply to replicate the conventional wisdom, or the accepted knowledge to date. Then we add to that the population measure. We add two terms, the population and the square of the population, because we found an inverted U-shaped relationship, that the likelihood of conflict rose as population went up, but then beyond a certain level it started to go back down again. This may be a function of the higher levels of urbanization at the high levels of population density. We haven't spent a lot of time probing the reasons for that. For the present study, this is largely a control variable. We're not trying to explain why population density has this pattern. We just want to control for it. So then the real work is being done by this rainfall deviation measure. So what we've done is we've taken a gridded earth science rainfall data set. For each month over the time period, we compare the observed rainfall with the long-term average. And we standardize that, so we measure it in standard deviations. And we can get a sum over the entire year for those monthly values. So if you have a very positive high sum of those deviations, it means you've had a lot of extra rainfall compared to normal. If that number is negative, it means that you've had a low amount of rainfall compared to the average. So then what we would expect, given our hypotheses, is that the coefficient should be negative, that the wetter the observed rainfall compared to normal, the lower the risk of conflict outbreak. And this is in fact what we observe. The significance is quite high. It's higher than any of the other socioeconomic measures. We experimented with different lags, and the strongest relationship was with a 1-year lag. So for our rainfall measure, the deviation from normal 1 year ahead of time is the strongest predictor of the likelihood of an outbreak of an internal political conflict in a country. What we found was that this relationship was true only for the high-level conflicts, with at least 1,000 battle deaths, more or less equivalent to a full-scale civil war. The low-level conflicts did not have this relationship to rainfall. We're doing some more work to try to explain this pattern. For me personally, it was the opposite of what I expected. I thought that rainfall would be a fairly marginal relationship, if any, have a marginal relationship with conflict, that people would be mainly fighting over other things that would dominate any kind of signal from rainfall. So if it had a statistical relationship, it would be at the low-level conflicts, not the high levels. This wasn't what we found. Our working hypothesis is that a severe shortfall in rainfall affects the marginal incentives of rural populations when they're facing a choice as to whether or not they want to join up or not with an existing rebellion. In a rural agricultural community characterized by high levels of poverty, if the rainfall shortfall is severe enough, the return on labor from farming gets close to zero. And therefore, in a comparative sense, the return from labor associated with joining with the rebel forces becomes more attractive. This is not meant to be deterministic. It doesn't mean that we know the threshold at which a given family will send someone to join the rebels. But at the margins, on average, it's going to have that effect. And again, we haven't proven that hypothesis. That's a mechanism that's consistent with the data that we found. This shows the data in aggregate to give you a sense of how substantively significant the relationship is. Across this axis, we quantify the deviation from normal. So right in the middle means you are normal. To the left, you're far below normal in terms of rainfall. To the right, you're far above normal. And this is the risk of escalating from a pre-existing low-level conflict. So we filtered out the regions that are at peace. And we're asking how many of those grid cells that are experiencing a low-level conflict escalate the next year to a full-scale civil war. So on average, around 12 or 13% of those do that. But if you're in the driest decile of the grid cells, that risk almost doubles to about 23%. And interestingly for me, the risk actually dampens as you get wetter. So you have, this was also unexpected for me. I thought if there'd be any relationship, it would flatten out here. But there's an apparent pacifying effect of rainfall from the data. This is just a zoom in on a microcosm of the case of Nepal. This was a civil war that caught a lot of people by surprise. There's been a lot of post-mortem studying of this case to try to come to grips with it and explain it. We just run our data through it to see what it says. So we've taken the country of Nepal, divided it into two parts, where the fighting was especially intense and where the fighting was largely absent. And we've plotted rainfall over time, from 1979 till the time of outbreak in 2002. For most of this time, you have a kind of typically almost random variation around a mean. And there's no terribly significant difference between the zone that ended up being in conflict and the zone that remained at peace. But beginning in the late 90s, you have two things going on. First, the entire country stays significantly below normal for an extended period, year after year. And the zone that ended up having the conflict break out drops significantly below the rest of the country for that entire period, and drops to a level that it had never experienced since the satellite data had been collected. In the global terms, this average of -15 is extremely low. This is a very sharp negative deviation from normal rainfall in Nepal. So again, this doesn't prove that we found an explanation for why the conflict broke out in Nepal that's driven by rainfall in a deterministic sense. But it's suggestive that the dominant explanations that have centered around patterns of growing regional inequality may in part have a climatic trigger to them. Most of what's been published about the inequality connections to the conflict take inequality as almost an exogenous feature or a political feature. We're suggesting that there may be a climatic connection to that as well. Just briefly, we've also taken river basins in Africa as the unit of analysis and just asked, are there any characteristics of the river basins that might help account for the different patterns of violence across the river basins? The signals seem less strong here. They are roughly consistent with the general argument, though, that water does matter. The map on the left shows the number of conflict years aggregated by river basin. So you're used to seeing that by country, but with the subnational conflict data, we can aggregate it to any unit we want. And on the right is the surface water runoff data from Charles Vörösmarty's center. So we see a significant but modest relationship between these two things. This shows the general correlation controlling for other socioeconomic factors between runoff and conflict years. And the basic story is that there's a handful of very wet river basins that seem extremely low in conflict intensity. And the general tendency is that as you get wetter, there's less years in conflict, fewer years in conflict. But it's not a gigantic effect. So then briefly, I just wanted to show a couple of illustrations for how it might be possible to put this knowledge to use. There's a lot of people trying to create conflict early warning systems, and so I just listed a handful of examples up there. Some of these are making some use of climate information in their work. But in general, when you look at the conflict early warning landscape, the general pattern you see is one of very little attention to climate and water. And so we think that the knowledge base is solid enough to make a case for at least paying attention to climatic variability and water issues systematically when you're doing conflict early warning. So if you're starting a conflict early warning system from scratch today, there's really no excuse for leaving climate out. So this is a very preliminary proof of concept. We've just spent a couple of months pulling this together. This is not a finished product. This is just to demonstrate the kind of thing that we think more people ought to be doing. We took the crisis group's watch list from November 2006, and we just made it into a map. It took a couple months to do that. It was frankly kind of disappointing and surprising to me that this didn't already exist, that there's not an official repository of conflict hotspots in map form. But in a couple of months' time, with a lot of student labor, we were able to get it done. Relief Web was the most valuable source, but there are other places that had this map information out there. And so we get a map that looks like this. The red lines are those places on crisis groups' watch list. There's a lot of different reasons you can get onto their watch list. So it doesn't mean people are shooting each other here. There may be forced migration going on. There may be refugee camps. There may be riots. But these are areas that someone has decided need scrutiny because of conflict potential. And we've simply overlaid these with the monitoring of rainfall that's going on using the combination of ground stations and satellite data sources. The very brown areas are highly below normal, so you see parts of West Africa like that. And the very bluish-greenish ones are significantly above normal. This is for the last 12 months, integrated over that whole period. This is the last 6 months, so you see the picture changing a little bit. And then the last 3 months. So what used to be a big dry zone here has now gone away because the rainfall has caught up or even surpassed normal, so you now have flooding going on in parts of this region. For the relief workers in here trying to deal with these crisis situations, the flooding is just as important to know about as the drought. This is just the same data, but just zoomed in for Africa. So you see Guinea and Cote d'Ivoire are areas where you have consistently over the whole time period, 12 months, 6 months, and 3 months, an overlap between extreme dryness compared to normal and existing watch list situations. So if I were trying to implement the peace accord in Cote d'Ivoire, for example, I would find this information relevant. That rural livelihoods in the north may be at risk because of this fairly consistent, strong signal from rainfall. If you take the whole data set and add up the numbers, these are the regions that emerge as having significantly dry rainfall spells and overlap with the crisis groups watch lists. So there's a lot of reasons why it makes sense to keep doing this in an operational sense. I think first, the most obvious one is the people who are engaged in prevention, preparedness, livelihood generation, and so on in these conflict regions probably can do a better job by knowing the rainfall patterns because the connections are so strong. In some cases, they're lucky enough that they already know this information, but across the board, that's not the case. In addition, in some places and under some circumstances, the ability to engage in long-range forecasting becomes quite high, especially in an ENSO, an El Nino year. And so this becomes additional information that can help fine-tune your conflict early warning. By putting everything into a spatial context, it lets you do a lot more than you can if you just are staring at a list of locations in a table. There's multiple hazards that people can be exposed to, landslides, pests, disease, and so on. If you see these on a map, you can see where they're contiguous, and you can understand risk in a different way. In addition, there's other watch lists that are out there. People tracking outbreaks of new diseases, people tracking endangered habitats and critical species, and so on. And being able to overlay these things spatially lets you uncover risks in new ways that you can't understand if you don't have the information spatially. And then finally, the climate scientists have gotten very sophisticated at understanding how climate proceeds in a potentially nonlinear manner. But our study of the impacts of climate change remain fairly crude and mostly linear. It's at least possible that a climate change world is going to have increased stress of the sort that we've shown historically elevates the risk of civil war. And so it's at least possible that a climate change world will have new patterns, perhaps greater frequencies of civil wars. These things are largely not discussed in the climate impact community. By putting the Civil War and the conflict information in a spatial framework, which the climate modelers are accustomed to, you can at least begin having the discussion about what those interactions are likely to be. So we started showing how the the starting point from speculation about water and conflict was a little bit simple-minded, but the advances in availability of data and analytical methods have made it possible to get more sophisticated about exploring the connections. And that if you actually look at the empirical record and you put the two kinds of data sets together, you can make a pretty strong case that water is related to conflict, but not necessarily in the ways that people were guessing 10 or 15 years ago. And finally, we've tried to make a case that this is useful information, that you can actually do something that'll potentially make the world a better place. And now we're ready for questions.
Terrific. Terrific. Well, thank you, gentlemen, all three of you, for really obviously well-coordinated set of presentations, and one that really built on theoretical and data and then putting it all together. So thank you very much for that. We'll turn now to discussion. I ask, as I did before, that you use a microphone to pose your question so we can capture that. And who would like to start us off? Yes, please, Stein.
Stein Tønneson, International Peace Research Institute, Oslo. I have two questions that are interrelated. And the first is how you handle the seasonal variation in rainfall. I mean, the difference between the expected variation and the unexpected variation. And the other question has then to do with military strategy in ongoing wars, where armies normally plan their attacks and their mobilization of soldiers as well in relation to the expected seasonal variation in rainfall, because in the dry season you can move more easily, and it also has to do with temperatures. And there is a difference between government forces and rebel forces, often because the government forces are more mechanized. Are these military factors also taken into the consideration in what you are doing? Let me just add that I was fascinated by this. There is enormous potential, I think, for making more sophisticated models that we can use once we get beyond the nation-state straitjacket.
On the seasonal variation, we've tried to implement the need to account for seasonality in a fairly simple but responsive way. So the essential trick is to calculate for each month the observed rainfall as a function of normal rainfall for that month. So in terms of what was expected versus what was actually received, we're measuring exactly that. Now, a more sophisticated way to account for seasonality would be to take into account the growing seasons, the explicit growing seasons. So a deviation during a growing season would count for more than a deviation outside of it. We're not yet doing that. In our long-term work, we hope to do that explicitly. I think that the way we've done it seems to work reasonably well, but it's not perfect. The people who do food security modeling, the famine early warning system, for example, they explicitly take that into account. It requires a lot more information to do that fully. They don't cover the entire world, so we can't simply use their measures. But I agree that that's the kind of thing that would be ideal. The military strategies, we just haven't addressed it at all. So if there are some simple ways that we can take into account possible variation in whether military strategies are going to be influenced by rainfall patterns in different places, we could experiment with that. But at present, we haven't.
Right. Can I amplify a little bit on the climate variability or the seasonal variability question? If you look at this from the standpoint of available water resources, there are two things going on. First of all, there's the local scale climatology and expected normals. But in addition, you have the delivery of important water supplies, particularly in arid and semi-arid areas that flow through rivers, that are basically the headwaters are generating water, excess water, in some cases hundreds if not thousands of kilometers away. And the societies that are dependent on those particular water supplies are going to be sensitive to changes not only in the local supply, but this far field supply as well. And when we've done our analyses on Africa, an initial set of studies, we've seen that the variability in the fresh water supply through the rivers is actually a more critical determinant of the variability question with respect to supply than what's happening locally. So we have to take those two perspectives into account. Gentleman in the back.
John Patch, I'm from USAID. I had a question, or maybe it's more of a comment, about looking at the issue of water. And do you think you'll be able to integrate concepts of land degradation and loss of soil fertility into your models as you develop these? Because not only do you have more variability, but you have less soil water holding capacity. And so the natural resource base of agriculture is being degraded as well as having greater climate variability, which could lead to more conflict.
I guess the answer to that is yes. And in fact, this very morning we were talking about how we could bring in some key data sets having to do with agricultural and food security, and on this very issue, the question of depletion of nutrient stocks and soil fertility questions and degradation came into our discussion. So that's a yes. It's a good idea.
Can I just build on that and ask you to amplify on where you see yourselves going from here with what resources that you have and what you would do with additional and follow-on resources, and also some sense of when we can expect to see some of this in print so it can be cited and more easily circulated.
Currently, we have money to do quantitative data analysis for Africa from the National Science Foundation. What we would like to do is quantitative analysis for the entire world, and we'd like to balance that with qualitative analysis, in-depth case studies, some of which, sometimes a case study is an easy thing you do at the end. These things are not easy case studies to do, to actually trace through the causal dynamics in a given place and to show how the water dynamics interacted with the political and livelihood dynamics. In addition, across the board, we would like to build up a more sophisticated capacity to model essentially the interaction between climate variability and human livelihoods than we currently have. So it requires things like getting the soil question right, the whole agricultural system right, and the kind of regional transfer issue, both explicit water transfers as well as livelihood transfers, where the job opportunities are in space. Until we can do that, it's if we could do that, we would have a more sophisticated explanation of the conflict patterns. But I'm sure my colleagues have a different set of wish lists as well. I think we plan to get some papers out fairly quickly, and this is a set of questions that have been attacked by a number of different people. So there's some additional PRIO scholars that have been publishing on similar things, and some of those articles are coming out relatively soon.
If I can follow on to that, we held a conference at PRIO jointly with the Norwegian Climate Research Institute on climate change and human security a year and a half ago, and some of the papers there on climate change and conflict are coming out in a special issue of the journal Political Geography in the fall. And some of those papers take a disaggregated approach and try to do some of the things that we've been talking about here. I think one of our priorities would be better data sets on conflict. We have state conflicts, both intrastate and interstate, down to a level threshold of 25 battle-related deaths per year, covering the entire period since from 1946 until today, and routinely updated annually. We have data on non-state conflicts that I talked about in my presentation only for 4 years now, maybe 4 years. And that's also being updated annually, but backdating that to, let's say, covering the entire post-Cold War period or the entire period since World War II will be a major effort. And as part of that, we're also looking at what is something called one-sided conflicts, where the government may or may not be a party, but one of the party, usually the victimized party, is an organized group. In other words, genocide, politicide, was also be called democide. And there is a data set from the Uppsala Conflict Data Project going back to 1989, but again, it would be nice to have that extended to cover the entire period since World War II.
Have you convinced the Norwegian Research Council to fund that yet?
No.
Okay, yes, John.
Wonderful presentation. Chip Dimon from OSD Policy Planning. Marc, a question for you. I appreciated your linkage between drought and a year later an increased chance of conflict. Have you looked a step farther to see if once the weather patterns return to normal, if that has a dampening effect on the conflict or a mitigating effect on conflicts? Thank you.
We haven't looked at it because for theoretical reasons it seemed that we know that once a conflict gets started, it's very, very hard to stop. And that the factors that are associated with bringing a conflict to a stop are very complicated and frankly fairly poorly understood. So it seemed extremely unlikely that rainfall would have a measurable signal in such a chaotic, unpredictable environment. But I have to say that every place I go, I get asked this question. So I think we just have to do the test and see. I don't expect to see a relationship, but if there is one there, then we'll find it and let you know.
Perfect. Yes, John, here.
Thank you. I'm John McCormick with the Energy Policy Center. I want to thank you. This is a marvelous presentation. If I walked into the room, though, in the last half hour or so, I'd wonder if you were trying to get an estimate on what the United Nations peacekeeping forces budget would be in 20 or 30 years. And obviously, the issue is maintaining civil society in areas of the world that are already stressed. So I'm wondering then, Dr. Gleditsch, if you could sort of look at worst case possible, and that is in the let's say the Himalayan glaciers more rapidly melting, and that's the headwaters for 5 major rivers that provide water for, what, 500 million people, 6 or 7 countries. Could you look at worst case possible, and not in terms of trying to project, but in terms of trying to say, this is even more amplification for how the world must tackle mitigation, because what you're really sort of talking about is adaptation. And I think we need more worst case so that the world can open its eyes to what the future might be if the Himalayan glaciers do in fact melt back.
Yeah, I'm not sure I completely agree with that. First, let me say about the climate change literature that the IPCC reports on climate change, of course, are extremely impressive when it comes to the natural science built on hundreds of peer-reviewed studies. Of course, disagreements remain among scientists, but the scientific community is moving towards much more of a consensus on the nature of the changing climate and the human contribution to that change. When you look at the work on the social consequences, it's much less impressive. And particularly, I've tried to look at what the IPCC reports say about conflict. And they drop a few remarks here and there built on, I wouldn't even say second-hand, but third-hand literature and very speculative comments. Same goes for the Stern report. Very impressive on the economics. very spotty makes a couple of remarks about migration and conflict and so on, which are not really built on any consistent research program. So I think that's one of the contributions we'd like to make, although this, what we're discussing here should not be seen as simply another climate change project. But that's one of the things we should be looking at. Now, do we need worst cases? I guess they're useful, but we also need to look at the adaptation and the whole question of economic development. As countries get richer, they may be better able to handle some of the transitions involved in climate change. As hopefully governments become more competent, they're also better able to handle these, and I think we need to factor that into the discussion. Of course, if we do not succeed in economic development, if we get more incompetent governments, then of course the worst case scenarios will be much more probable.
Okay, Peter.
Thank you, Peter Utro from the Environmental Protection Agency. That was, in fact, a lovely series of integrated presentations. I had a question which I think was for Dr. Levy, but I sort of feel saturated with data and pretty colors, so I've forgotten. Was it you that spoke momentarily about normalizing this against population? And I honestly did not understand the point you were trying to make there. And I am curious about the extent to which this data has in any way been run against population numbers or demographic numbers in terms of age distributions.
So it's a two-part answer, and the second part is to hand off to Henrik Ordahl. The first part, on our gridded data, we find, well, if you operate in a country universe where the world is organized into countries, and Algeria is next to Albania, and you don't have this spatial stuff mixing everything up, then you don't have to, it's perfectly possible to run regression models that explain the outbreak of civil war that ignore population altogether. Because there's a degree of similarity. The units have a lot in common. Some countries are bigger than others, but and you can put population in, but you don't have to, and you can still get understandable results. The first thing we found when we went to this gridded approach is that just didn't work at all. There's a lot of grid cells in the world, unlike countries in the world, that have no people in them. And so the business of trying to predict whether that unpopulated plot of land is going to have a civil war was obviously silly. So we realized immediately that we had to control for population so that we weren't trying to explain civil war that there were no people to fight anyway. And that so to do that, we had to look at, well, what's the relationship between gridded population and gridded conflict? And we found this inverted U, where it peaked at a fairly high level. I think basically near urbanization. Now this does not explain, the causal effect that population density has on propensity to fight. It's strictly a control variable because of our gridded unit of analysis. Now there has been a lot of work about population dynamics and country propensities, and even subnational work that has brought in things like youth bulge and age structure. And Henrik is the one who's been doing the most of that recently. I don't know if you want to summarize that.
Just a short follow-up on that. I completely agree with Marc that we should be careful about drawing any conclusions about population pressure and conflict in this kind of analysis. But there are, a lot of other ways we can look at that, and we both have cross-country studies. I've done one on population pressure and armed conflict on the country level, finding very, very meager results for any kind of relationship. But I've also done a subnational study of India, comparing Indian regions, where there is some more support for the idea that some of these more subtle population pressure mechanisms may have something to do with different forms of political violence. I've also unfortunately, we don't have the kind of disaggregated data on age composition that would enable us to do an analysis in a grid format, which would be great, but unfortunately, no one has funded that yet. Again, cross-national studies do suggest that there is a relationship between very young age structures and a somewhat higher risk of armed conflict and other forms of political violence. And I've also been able to find that pattern locally or regionally for my case study on India.
Do we have other questions or comments for the panel? Yeah. All right. Well, I think it's terrific that you've been willing to come and share work in progress, as you said, and even if it's hearing some of the same questions again for multiple times, suggesting that there are other things to run. Hopefully, there's been some useful feedback. I urge you all to stay in dialogue with our speakers on this and bring your insights to bear. As I mentioned, because we are webcasting the meeting, the video of this program, as well as a write-up, and then hopefully also the slides, will be attached and found at the Wilson Center's website, so that you can share this with others and